We're going to talk about section 7.5 in our book, Numerical Integration. We know that any continuous function is integrable. That is, we can find the area underneath its curve. But some functions do not have what we call closed form solutions. So things like e to the x squared and sine of x squared, and there's many others. We can't write down a function whose derivative is e to the x squared, nor can we find one whose derivative is sine of x squared. But their graphs are continuous curves, so we can figure out how to find the area underneath those curves. So we have a need to come up with ways to find numerical approximations for definite integrals that are both accurate and efficient. Now, we have seen left, right, and Riemann and midpoint Riemann sums, and we're going to work now on another method, one that's called the trapezoidal rule. So some of you may have thought of this before when we first talked about approximating areas under curves using rectangles. So if we have this green function y equals f of x, and we're going from a to b, then we say we partition that segment, that interval from a to b into n uniform width subintervals, and that's what you can see in the blue. When we number those, x sub 0 is going to be a, the left endpoint. X sub 1 will be the first tick mark to the right, and that counting will leave us with x sub n, the last one being b. Now, the area of a trapezoid is 1/2 the sum of the bases times the height. So, if we're going to approximate our area under the curve here using trapezoids, we're going to find the area of these n trapezoids. So I'm going to slide up here a little bit and see if we can figure out what that's going to look like. Now, this first trapezoid, so we're going to imagine coming up here, and this is how we're going to form our trapezoid. We're going to pull that out and turn it on its side so it looks something like that. So that means our first trapezoid is going to have this base is going to be f of x sub 0. That's that value of the function at x sub 0. And this base is going to be f of x sub 1. And we're going to multiply that by 1/2 from our formula. And then the height is going to be our delta x, which we can see right here, and that's going to be b minus a over n. So there's our area of our first trapezoid. Now the second one, we're going to again have the 1/2, and we're going to again have that b minus a over n as the height. Now that second trapezoid up here, so we're going to come up there and then connect those with a straight line segment. Now its first base is the same as our second base on the first one. That's going to be f of x sub 1, and then we're going to get an f of x sub 2. Let's do one more of these. So that third one is going to be 1/2. We're going to get another f of x sub 2 plus an f of x sub 3 times a delta x, which is b minus a over n. We're going to run that out to the nth rectangle. Now that last rectangle is going to have, or not rectangle, but trapezoid is going to look like this. So if this is x sub n, that is going to be x sub n minus 1. So we're going to get 1/2. We're going to have f of x sub n minus 1, that second to last tick mark, plus f of x sub n, that's really b, and then we'll have our b minus a over n. So when we factor these out, we're going to have all of these have 1/2 in them. All of those trapezoids have a 1/2, and they also have a b minus a over n in them. So if we factor those out, we get a b minus a over 2n. Now, what we see that's left is we're going to have just this f of x sub 0, but we're going to get an f of x sub 1 from here and another f of x sub 1 from there. That's going to make 2 of those f of x sub 1s. We are also going to get an f of x sub 2 and another f of x sub 2. So what this is starting to look like is one of the f of x sub 0s. Oops, I don't know what happened to my pen there. Oh, it stopped writing for a moment. I don't know why it did that. Oh, I know. Let me screw the tip on there better. So we have one of those f of x sub 0s, 2 of the f of x sub 1s, and 2 of the f of x sub 2s, and we'll continue like this, 2, 2, 2, 2, 2, until we get to the very end. And at the very end, we're going to have that, and there will be one in the trapezoid immediately before that one. So that's going to be our 2 times the f of x sub n minus 1, but there will be only one of those f of x sub n's because there's no other partner with it. So that's going to be an f of x sub n. So our formula is just what we see there. You're going to get this b minus a over 2n, then you're going to get one of the first ones and 2 of all of the others, 2, 2, 2, 2, 2, until you get to the very last one, in which case you'll just get one of the very end one. So that is our formula for our trapezoidal rule. So I guess I'll say that is our trapezoidal rule for when they are uniform with trapezoids. Okay, so the rule is that formula for evaluating those trapezoids. So here's how it looks in practice. Suppose we want to approximate the integral from 1 to 2 of x squared dx using the trapezoidal rule with n equal to 4. So we're going to use 4 trapezoids. So in the picture on the left, you can see here's our parabola y equals x squared drawn in yellow. We have the interval from 1 to 4 is labeled down here, or 1 to 2 rather, and we have tick marks representing 4 uniform width trapezoid. So what we're going to do is use our formula. So we're going to go b minus a over 2n. Since we have 4 trapezoids, we're going to go f of x sub 0, one of those. We're going to go 2 of the x sub 1s, 2 of the x sub 2s, 2 of the f of x sub 3. So that's going to be, let's see, f of x sub 0. There's 1, 2, 3, and then we're going to get 1 of the f of x sub 4. Now these values for x sub 1 and so on are going to be where these tick marks fall. So this is going to be b minus a is going to be 2 minus 1 is 1. 2n, since n is 4, is going to be 8. And we will have f of 1, I'm going to write it down in function notation, plus 2 times f of, that's going to be 1 and 1/4, plus 2 times f of, add another fourth to that, is going to be 6/4 or 3/2, plus 2 times another 1/4 plus the 6/4 will make 7/4, and then 1 of the right endpoint. So if we plug that in, we're going to get 1/8 times f of 1 means we're going to plug 1 into our x squared function. That's just going to be 1. We're going to get 2 times 5/4 squared is going to be 25/16, plus 2 times 3/2 squared is going to be 9/4, 2 times 49/16, and 2 squared is 4. Then that's going to be kind of a mess if you do it with your, if you add the fractions, but you can go ahead and use your calculator. As fractions, that's going to end up being 75 over 32, or as the decimal equivalent, that's going to be 2.3475. 2.3475. So either of those answers will work for our trapezoidal rule approximation. Now, We could actually do this one because we could say the integral from 1 to 2 of x squared dx is going to be 1/3 x cubed going from 1 to 2. So 2 cubed is 8/3 minus 1/3 is going to be 7/3. So if you want to see what the error is, so the error would be the actual value, say 7/3 minus the 75/32. And then if you want the percent error, just for an idea of how accurate this might be, if we took that error, so I'll write it as the 7/3 minus the 75/32 all over the actual value, if you change that to a percent, it turns out it's 0.446%. 0.446%. So that's just an idea of that kind of accuracy. Understanding, x squared is a curvy function that we're trying to approximate using these little straight line segments, and we only used 4 trapezoids. So it's going to be a little better than the rectangles, but next year in BC we'll learn another method that's significantly more accurate than the trapezoidal rule. So then the question comes up in the blue here, is our approximation an overestimate or underestimate of our actual value? Well, we can see that we figured it out, but the idea here behind it is if we look at our original function, since it looks like that, if we imagine approximating something that is concave up using a trapezoid, we're going to get an overcount of that area, as opposed to if we were trying to, say, approximate a function that was concave down using a trapezoid, we would see that we would undercount it because there'd be a gap there. So our approximation, because our original function is concave up, is going to be an overestimate. And the reason that we have to give in the eyes of AP is because our original function f is concave up. So remember that, so let me just change colors there. So let's just remember Riemann sums depend on increasing or decreasing. I'm going to say depend on f being increasing or decreasing. So an increasing function, for example, with a left Riemann sum will be an underestimate, and a right Riemann sum would overestimate that area. So in the case of Riemann sums, rectangles, if you're asked the question why is an approximation an overestimate or underestimate, your answer has to address is f increasing or decreasing. If you are asked the question, is a trapezoidal sum going to be an overestimate or underestimate, the justification, the reason, has to do with the concavity. Okay? And interestingly enough, our book, not all books talk about that, but our book mentions that a Riemann sum works the opposite of a trapezoidal rule. So whereas a trapezoidal rule will overestimate a concave up function, a midpoint Riemann sum will underestimate a concave up function and overestimate a concave down function. Okay, now this we need to talk about. A uniform width trapezoidal rule almost never appears on an AP exam. So the formulas aren't going to be much help. That's why they don't include them. They don't want students to program in the trapezoidal rule into their calculator and be able to do the problem, just using it as if it was a computer. So more typically, when you're asked a trapezoidal rule question, it'll come from a table of values like you see here, and you will notice that these are not uniform width trapezoids because our delta x here is going to be 1, and our delta x here is going to be 2, and the delta x here is 3. So in a non-uniform width partition, the formula for the trapezoidal rule, that b minus a over 2n times f of x sub 0 plus 2, 2, 2, 2, 2 plus f of x sub n, goes out the door. Instead, what we have to do is find the area of the individual trapezoids. So that's what we're going to do here, is approximate our integral using 3 trapezoids. Now you don't have to graph this, but I'm just going to plot some points here so you can kind of visualize what is happening here. So we're going to say that, there's 2, and here is 3, and there's going to be 5, and here is going to be 8. And I'm not going to be concerned really about the accuracy of these heights, but we're going to say here's 4 for 2, and then up to 6, and then way up to 10, and then back down to 7. Now, what we see is that our trapezoids are going to look something like this. So that, whoops, I didn't quite go to the right place there. Let me see if I can fix that, so at least our height is above our x value. So it's going to look something like that. So that's just to help imagine what our formula is going to look like. So we are going to say that our integral from 2 to 8 of f of x dx is going to be approximately, we're going to go 1/2 times the sum of the bases. So our first 2 bases of that first trapezoid are going to be these y values. So the y values, the f of x values, the values of the function, are the bases of our trapezoid, and our height of the trapezoid is going to be our delta x, which in this first case is going to be 3 minus 2, which is 1. And then the second trapezoid will get its bases. Remember, this one is a shared base here, and this is going to be a new base. So we're going to kind of recycle the 6 and put it together with the 10. And its height is going to be that delta x, which 5 minus 3 is 2. And our third and final trapezoid will share this same side, so that's going to be a 10. And then its other base is going to be our 7, and its height is going to be this delta x, which is going to be 3. So that's how we will get our values for our trapezoidal rule, and then we just do the arithmetic. So we have half of 10 is 5, half of the 2 is 1, 6 plus 10 is 16, and then this gets a little ugly. We got 17 times 3 is 51 halves. So that's going to be 51 halves, which I'm going to think of as being 25 and 1/2. So that's going to be 5 plus 16 is 21. 21 plus 25 is 46 and a half. That's how you would approximate that integral using a trapezoidal rule. That's a more typical AP style question on the trapezoidal rule. So our book points out that the trapezoidal rule is actually the same thing. It's equal to the average of a left and right Riemann sum. So just to remember, let's see if we can do a left Riemann sum. So now we're doing the base times the height of our rectangles. The base is going to be the delta x, which is going to be that 3 minus 2, and the height is going to be the left one, that's going to be the 4. And then the base of our second rectangle is going to be the delta x, which is 5 minus 3, and the height is going to be that left-hand f value of the function. And our third rectangle is going to be that 8 minus 5, and then times the 10. Whoops, I didn't mean an equal sign yet. So times 10. So that looks like 3 minus 2 is 1, times 4 is 4, and 5 minus 3 is 2, times 6, whoops, is going to be 12. 12, and the 8 minus 5 is 3, times 10 is 30. So that looks like 30, 42, 46 for our left Riemann sum. The right Riemann sum, we're going to have the same delta x, so 3 minus 2 is 1, whoops, 1, and the height is going to be that second value, which is the 6, and the second rectangle will be the 5 minus 3. My left hand keeps hitting that in a place that I don't want to. So 5 minus 3 is 2 times its height, which is going to be that value of 10, the right side of our rectangle. Then the 8 minus 5 is 3, and we're going to use the 7, the right-hand side. So that's going to be 6 plus 20 plus 21, so that's going to be 41, 47. So if we average those, we'll get 46 plus 47 divided by 2, that's going to be 80, 93 divided by 2. Half of 90 is 45, and half of 3 is 1.5, so that's going to be 46.5, and as promised, the same as our trapezoidal rule. All right, very good.